We've talked about percent composition, which tells us the relative amount of an element in grams compared to the whole compound in grams. Sometimes, rather than telling a percent of an element within a compound, we're interested in telling the amount of a compound within a mixture. In other words, concentration. The most common unit of concentration in chemistry is molarity, and the associated unit is called the molar. A solution is the same thing as a homogeneous mixture. It does not necessarily have to be a solid dissolving in a liquid. It could be liquid dissolving in liquid, or liquid in gas, or solid in gas, or gas in gas, etc. No matter what type of solution it is, whichever substance is present in the greatest number of moles will be called the solvent. Often our solutions will be made with water as the solvent. For example, when we dissolve salt into water, the water is present in a greater number of moles, so it's the solvent. The substance present in the smaller number of moles is called the solute. In this figure, the sodium chloride is the solute. There's less of it. Together, the solvent plus the solute makes the solution. The solution is everything together. Our definition for molarity is moles of solute divided by liters of solution. The moles of solute is essentially the part, and we're dividing that by the liters of solution, which is the whole. We can write an abbreviated equation. Capital M for molarity equals MOL for moles divided by capital L for liters. Please do not use a lowercase m to abbreviate either molarity or moles. A lowercase m is used for other things in chemistry, such as a different type of unit called molality. We can also solve for either moles or liters by rearranging our molarity equation. As we do this, our volume must still be in liters. You cannot use microliters or milliliters with any arrangement of this equation. You can only use liters because the definition of molarity is based on liters of solution. If you want to solve for liters, you need to get liters by itself on one side of the equal sign. You can do a little math trick and exchange something in the numerator on one side of the equal sign with something in the denominator on the other side of the equal sign. Molarity and liters switch places, and you get liters equals moles over molarity. You could also work the rearrangement longhand by dividing both sides by molarity and multiplying both sides by liters. Please go through an algebra tutorial if this doesn't make sense to you. If you want to solve for moles, you need to get moles by itself on one side of the equal sign. From the original equation, you can multiply both sides by liters. So you end up with moles on one side of the equal sign and the molarity times liters on the other side of the equal sign. Let's look at an example. We're trying to find the concentration of sucrose in a soda. We're given the volume of the sample in milliliters, and we're told how many moles of sugar are in that sample. We know moles and we have a volume. But in order to use our molarity equation, that volume must be in liters. To change our milliliters into liters, we multiply our milliliters by 10 to the minus 3 and come out with 0.355 liters as our volume of the soft drink. Now we can use our molarity equation. Molarity equals moles over liters. We plug in our moles, which is 0.133, and we plug in our liters, which is 0.355, and we come out with 0.375 molar as our molarity. Here's a second related example. We're trying to find how much sugar in moles is found in a sip of the soft drink from the previous example. Not the whole can, but just 10 milliliters of that soft drink. Because it's based on the previous example, we already know concentration. One sip of the soft drink has the same concentration as the whole can of soft drink, which is 0.375 molar. Again, anytime we use our molarity equation, the volume has to be in liters. We need to take our 10 milliliters and convert it into liters before we can put it into any rearrangement of our molarity equation. So we take our 10 milliliters and multiply by 10 to the minus 3, and it gives us 0.010 liters. So now we have a molarity and we have liters, which means we can solve for moles. We use our third rearrangement of the equation. Moles equals molarity times liters. We multiply our 0.375 molar times 0.010 liters, and that tells us that 0.00375 moles of sugar are found in that 10 milliliter sip of that particular soft drink. In our third calculational example, which is based on the previous ones, we have some sweet tea, and it has a different concentration compared to the concentration of sugar in the soda. The sweet tea's sugar concentration is 0.05 molar. Let's say we're on a diet and we want to find what volume of the sweet tea we can drink that will give us the same amount of sugar as the sip of soft drink from the previous example. In the previous example, our sip had 0.00375 moles of sugar. So we want to have that same amount of sugar, the same number of moles. We know molarity of sugar in the tea, and we have moles of sugar we want to consume from the tea. So we can use a different rearrangement of the molarity equation to solve for liters, which is volume. The rearrangement we need is liters equals moles over molarity. We plug in our moles, which is 0.00375. We plug in our molarity, which is 0.05 molar for the sweet tea. That tells us our volume that we're allowed to drink is 0.075 liters. Now the question's asking us what volume in milliliters has that same amount of sugar. We change our liters into milliliters by dividing by 10 to the minus 3, and that gives us 75 milliliters.